Hello, everyone. I would like to welcome Ms. Paola Bianchi. Paola is a senior data scientist at Sulke Engineering AG and has several years' experience in machine learning projects. She holds a PhD in computer science from University of Milan, where she conducted research in the area of formal languages and automata theory. She will be making her presentation on using AI for automatic hail damage assessment. Manually assessing hail damage on a car body is a tedious and time-consuming process. Paola presents machine learning solution of Zulke, which handles challenges like data scarcity and processing time constraints. Welcome, Paola.
Thank you very much. Welcome, everybody. So in the next 20 minutes, I'm going to present a project that we had at the beginning of last year with a client called PDR Team. They are a German company that is specialized in hail damage repair on your car. So the way it works is you drive your car to them, and they fix any dents you have on the car bodywork with these tools. Unfortunately, they don't do it for free. They want to charge you for it. And in order to know how much to charge you, they have to evaluate how many of these dents you have on your car. And you might think that it's not so difficult to go around the car and count them. But the issue is with some heavy hail storm, you might have hundreds of these hails and of these hail dents. And if you work in insurance, you might have some PTSD about last summer when there were a lot of hails, especially in Germany and in Switzerland. So yeah, there were a lot of cars that had so many damages. And counting manually all these dents takes roughly 30 to 40 minutes. So PDR Team came to us and asked us to automate this process. So they want us to estimate the number and the size of the dents. They want a very high accuracy. They want to reduce their processing time to 5 minutes in total. And we had 3 months to provide a prototype. So we had quite challenging requirements. However, PDR Team came prepared. They already developed this arc that you can see on the left. That's called Colibri. And this arc has 8 light stripes and 7 cameras. And these cameras capture videos of a car passing through. I hope that the video works. Perfect. And you can see when the car passes through, the light reflection bends a little bit around the dents. So it becomes very easy to see where the dents are if you look at the reflection of the light. So yes, this is the data that we work with, these videos, which is very nice because of this light reflection. The main issue is we had this project before that infamous summer, so we didn't have as much data. And yeah, this is maybe an understatement. We had 3 cars, and for each car we had only 1 video. And that's all the data that we had. So yeah, another challenge was, since we have these 7 cameras, we have from different cameras the view on the same car part. So we can detect the same dent from 2 different cameras, and we need to make sure that we don't count it twice. So given that we only had 3 months to complete the prototype, we decided to make our life a little bit easier, and we only considered 3 of those 7 cameras so that we could assign univocally each car part to a single camera. The other decision we made, also because of the lack of time, was to outsource the labeling. of the data. So we worked with a labeling partner to whom we gave samples of the video. So we gave them frames, and they labeled on these frames the bounding box of where the dents were. And this is the high-level steps of our solution, and a little bit of spoiler on how we implement them. So first, we're going to recognize each car part. In a second step, we will do a dent detection on the single frame for each of those car parts. Then we will aggregate those detections from the frame coordinates to a global coordinate system. And once we have this aggregated view of the detections, we're going to merge the overlapping detections and estimate the size and the number. So we're going to go into details of each of these steps, starting with the car part recognition. So since we cannot do fancy things like learning the shape of the car because we only have one video, we decided to use some markers, and specifically the Aruco markers. That are these square, funny-looking things that can be recognized very easily with standard libraries. So once we have the image, we know exactly which marker is where and what the size and the position is. So we place them strategically around the car, and we know that that is, for example, the perimeter of the roof, for example. On to the second step. For the single frame detection, we decided to use a pre-trained faster RCNN and fine-tune it with the video that we had. And as input to this network, we give chunks of the image, and we make sure that the chunks overlap a little bit. And this is because we want the network to learn where the dents are, but we don't want to penalize it if it doesn't recognize something on the border. And we don't want to miss that dent anyways, and with the overlapping, we are sure that it appears in another of the chunks. Okay, so the fact that we have only one video is also a challenge in the evaluation of the model, because if we use the video to train, then we have nothing to validate, nothing to use to do, for example, hyperparameter optimization. So we decided to be a little bit creative, and we thought, well, the two sides are symmetric, mostly. So if we flip one of them, we can kind of regard them as two videos of the same side, and we can use one for train and one for test. And for the top view, we do something analogous. We cut the image in half, and we flip one of the two sides. Yes, finally, about the frame detection, we noticed that sometimes the Aruco markers were confused with detection, with the light bending around a dent, because they have this white on black pattern. So one final thing that we did before the training was to mask all the markers, and we could do it automatically because they were automatically recognized, the position. And we did some standard image augmentation. So this is, in the end, the result of the frame detection. And you can see that some of the dents appear, well, most of the dents appear in more than one frame, some of them in consecutive frames, some of them disappear because they are between the lines and then reappear after a couple of frames. And also the shape of the car changes a little bit, depending whether it's exactly perpendicularly below the camera or if it's at the end of the frame because of the angle and the distance. So it's not so straightforward to track where a dent goes. And the solution we found was to use again the Aruco markers, and we used them to basically map the space. So we defined a triangulation of the space, and we define some global coordinates. Like we take one marker as a reference, and we basically average the distance of all the markers among themselves in all the frames, and we get the coordinate system on the right. So in this way, we can also have a view, for example, of the whole roof, even though the whole roof is never in any frame. And about the shape changing, if we have some detection in the middle, we can express this detection as a linear combination of the markers that define the triangle it's in, and we remap it in the global view as the same linear combination. So even if the shape of the car changes, it changes in the same way in the whole triangle. So it is still consistent. Yes, so once we have these detections in the global view, the idea is that whenever a detection the same dent appears in multiple frames, it will be remapped in the same point or in the same area of the global detection. So we can define a heat map of all the detections, and we fit blobs around here. So the idea here is if we have enough overlapping detections, we consider that a real dent, and whatever is detected just in one frame is most likely a mistake. And this way, the number of blobs is the number of dents. And we can also estimate the size, because we know the real size of the markers and how many pixels it is in the picture, so we can do the same proportion from the size of the circle. Yes, so this is the video of the detections in the global coordinate space. And you see, even if for example, the marker of the roof are not all in the frame, they are predicted. So there's still the triangulation reference. Yes. So this was the prototype that we developed. Of course, there's still much to do before it can be a full commercial product. First of all, we need to introduce the remaining cameras, because from the 3 that we have, we don't get the full view of the car, or even when we get the view of some parts, the light doesn't hit in the right way, so we don't see the reflection. And when we do that, of course, we have to handle the overlapping view and make sure, do some kind of aggregation, like we did like this, but from 2 different angles, which is, of course, more challenging. And another issue that we have, another thing that needs to be revisited is the amount of Aruco markers that here we had for necessity, because we didn't have enough data, but we have roughly 100 markers on a car, and of course that is not feasible in a commercial case. But with more data, we could do something more fancy, like learning, for example, the shape of the car, and having more data also will allow us to get reliable metrics, because right now we don't really have a proper test set. And the last thing I want to talk about is, I would like to go back to this constraint of the 5 minutes, because we had really a lot of data, and it was quite a challenge to get everything under 5 minutes, including generating the videos. And we had to find some solutions to reduce the time. One of them was to reduce the search space. So, for example, we don't want to even process a chunk that is outside of the triangulation, because that's for sure not in the car, that's for sure not of interest. So we only consider the chunks that are within the triangulation. And the second thing that really helped a lot was to deploy our solution as a series of microservices, each in their own Docker container, so we could parallelize each part. And many of these things are very independent, so detecting the dents on the roof or on the door is completely independent, so it can be parallelized. And we also use ready RDS queues for the messages between these services to ensure that this division wouldn't increase the time by adding overhead with the communication. Yes, so since I showed you the Mazda example throughout the presentation, I will end with one of the other cars, the Suzuki. And in the meantime, I will be happy to answer any other questions that you might have. And also, I would like to remind you that we are currently hiring. We're looking for data scientists, junior or senior. So if you're interested, just come to us, to our booth. Thank you.
Thank you very much, Paola. Thank you very much. It's one of the very rare and interesting cases with a lot of data, but very small sample size.
Yes.
Questions from audience?
So thank you very much for the talk. So I wonder, so here in your actually framework, you have a static detector and moving car. So I wonder, did you test the other way around? So you have a moving detector, but you have a static car. So in this case, you can portable device, so you can go different part of the city to get more data from different cars or whatever.
Yes, we thought about it. We didn't try it out in our case, but we thought about having a mobile app so that someone could actually walk around the car. Yes, that's of course more challenging because here in one view, the movement is more predictable, while with the moving around, you have to make sure that you actually cover everything. So there's a couple more challenges there. But yeah, that's something that will be even more useful.
Okay, thank you.
Thank you.
Thanks for your talk. I'm wondering, have you considered using more cameras to make 3D point clouds instead of 2D images of the car?
So internally, they had a project that was using this arc to build a 3D reconstruction of the car. And we thought about an alternative approach. So we deliberately didn't want to use that specific approach. It's also quite hard to have a proper 3D reconstruction of the car, especially when what you're interested in is a very small difference in the reconstruction. So you would need to compare a brand new car and a car with a small dent. So you have to be very precise in the reconstruction. We didn't do it. We know it's quite challenging.
Thanks a lot. My question is a bit related to the last one. I can see that comparing a whole 3D model to look for dents would be very hard to do. But from what my impression was that one of your main problems is to find the car's geometry. And just for that, to get the rough outline in 3D, 2 or 3 LiDAR cameras might really help instead of all these markers that have to be fixed on the car each time. Did you think about this approach?
We didn't for this prototype. We wanted to see if we could do it just with an image, with a 2D image, and what we could have with that. But yeah, I mean, our next step, our idea for the next step with reducing the marker was to learn the shape from a 2D image. But yeah, that's also another possibility, what you say, that's a good point. That could be also something that we might consider if we continue this project.
Yeah, I was mostly thinking about practicality in the garage. If you have to put 100 markers on each car,
yeah, it's absolutely not practical. Yeah, we know that.
Okay. More questions? I have maybe one last one then. Have you thought about, or did you think about using some form of synthetic data for scaling your images? Let's say, getting more data because you had very few cars.
We didn't really have, so we did some augmentation, like the very basics, the very standard augmentation, but not real synthetic data.
Okay. Thank you. Any other questions from audience? No, thank you very much again, Paola.
Thank you.
And we have something for you here for your hiking. Thank you very much.